What's up? Welcome back. In this episode, you'll see how to solve day 7 for the advent of code in 2023. This one's called Camel Cards. It is a simple version of poker. So we've taken an airship up, we're on Desert Island, and we're riding a camel with an elf. And to pass the time, we're going to play some poker. And our input is a bunch of hands, poker hands, where on the left side, that represents the 5 cards that we might receive. So this is going to be a 3, a 2, a 10, a 3, and a king. And on the right, that is the bid for the hand, apparently. Now we need to go through and figure out if each card in the hand is one of exactly one type. Each hand can be a 5 of a kind, 4 of a kind, full house, 3 of a kind, 2 pair, 1 pair, or high card. And so the first step is to go through these cards, figure out which type they are. Once we know which type they are, we will put them in order by type. And if there's 2 of the same type, then we're going to break the tie based on which of the hands has the highest card at the front or as the first card. And if there's still a tie, then we're going to look at the second card, so on and so forth. So we're just ranking by hand type, and then we'll break the sort order by the strength of each card. Let's grab our puzzle input here and get started. Okay, so we're going to open up main.rb, and we'll say that our input is equal to, like always, the input that we just got. And we'll say data is input dot each line. And to get back some hands, we want to go through data and we want to parse out the hand. And because each hand has quite a bit of data here, so there's going to be each card is going to have ranks and whatever, and then there's a bid. So I'm going to take each line and create a class that represents each hand, and we'll parse that into a hand object. Okay, so here we'll make a class called hand, and it will have some class method called parse. And instead of, oh gosh, GitHub Copilot's going a little crazy here. So we are going to get a line in, and what we want out is some cards. So that's going to be these cards, and then also some bid. So we need to maybe split the line, and we're going to get some like raw, like C and B for our bid. And then what we want to do is say that like our bid is actually going to be b.2i, and our cards are going to be each of the characters from the cards. Now, it may or may not make sense to split up and map those into their values at this point, but we're definitely going to want that later. So what I think it might make sense to do now is just, translate the cards into their numeric values. Maybe we can say .map do char, and here we're going to have a mapping between A points at 14. That's going to be an ace. King is 13. Queen is 12. Jack is 11. T is 10. And then otherwise, we're going to convert it to integer, and that should just give us back the integer value. And that'll be some cards. Now we'll initialize an instance of a hand with cards and the bid. And I think I also maybe want to pass in the raw line or something, or we'll pass this in and we'll call it the name, just so that we can like easily refer and kind of debug with that. It's just like easier to read if we have this full string. So it's just like a handy little thing there. All right, so now let's just print out hands at the bottom to see what we get. Ruby main.rb. Boom. All right. So we have the name 32T3K, 3210. So 3210, 313. That looks good. That correctly parsed our character representation of the cards into the numeric representation, and we have the correct bid. So now we've got all of our hands. The next step is to figure out how we want to rank these hands. What I wanted to talk about today is something called the comparable module, or the comparable mix-in that's available in Ruby. The way that this works is you can include the comparable module, and then you define this special method called the spaceship operator, or the spaceship, I don't know, we're doing like a operator overload here to define a method for the spaceship operator. That gives us a bunch of nice things. For example, then we can call something like hands.sort, and we should get back a sorted list of hands. If we run this now, whoops, let's see. So if we comment that out, if we sort, yeah, so comparison of hand with hand failed because it doesn't know how to actually compare those. So if we define this method here, so def spaceship operator of other with other, and for now, let's just say cards dot first spaceship with other cards dot first. That's going to compare the biggest card with the other biggest card. So now when we run this sort is working successfully because, or it's at least the method isn't raising an exception because now we have the spaceship operator defined and we can compare one card with another card. Now, what the heck is this thing actually doing? So let's open up IRB here and take a look. So if we have 1 and we compare that to 2, then this tells us, or this is going to return -1, 0, or 1, depending on the order. So here, if we say, let's see the comparison of 10 with 2, this is going to return 1 because 10 is bigger than 2. This is returning -1 because 1 is less than 2. And if we put in the same number, you can probably guess what's going to happen. In this case, we're going to get back something that says these two things are the same or they're equal, so that we should get a 0. You can imagine in the most naive implementation of sort, right? If you're bubble sorting, you just go like pairwise, and if the one on the left is smaller than the one on the right, then they're good. So if it's -1, they're good. If it's 1, I need to swap the locations of the two and then move to the next one. And if they're out of order, then I need to swap. So 1 kind of means they're out of order. -1 means they're in order. And so what we need to do is figure out how we can implement this spaceship operator and do something in here so that we get back hands in rank order, depending on what type of hand they are. And then with that tie broken based on the strength of the cards in the hands, almost like in alphabetical order. So we'll implement a method here called type. And type is going to tell us whether or not, if it's a 5 of a kind, 4 of a kind, full house, et cetera, et cetera. So we want to go through all of the cards and figure out if we have 5 of a kind or fewer, right? And so one way that we can do this is by creating a counter. Yeah, I think what we want to have is a dictionary of the cards in our hand pointing at the number of times that card occurs, and then we can inspect the values to see, do we have, yeah, let's just get into it. So let's say we have this card counts, which is going to be, wow, is that going to work as we expect? Cards.group by itself. Okay, and then P card counts. Let's just see if we can get hands.map. Okay. We want to see both the type, ph.type, and we want to see the name and type, so that we can kind of debug and inspect and see if this is working as expected. Here we have 3, there's 2 3s, and the rest, there's 1 of each. So there's 1 2, there's 1 10, and there's 1 king. Okay, that's great. And then here we have 3 5s, a T and a J. 3 5s, a T and a J. Perfect. Okay. That's very cool. So now we have card counts. And what we want to do now is, see if there's any 5, then we want, if there's any values in our card counts where the value is 5, that means we have a 5 of a kind. So here we're going to return some value, but for now, let's just say 5 of a kind. Else if the card counts are 4, then we're going to have a 4 of a kind. Else if the card counts if any of them have 3 and 2, so if there's a case where we have a value that has 3 and a value that has 2, that means we have a full house. If it's 3, we have 3 of a kind. If it's 2, it's a pair. Otherwise, it's a high card. Okay, so this should give us back the type at least. So let's just see if we run this. So this one is a pair. This one is a 3 of a kind. This one is, this one's actually 2 pair, right? King, king, and 7 7. So we need another thing here, 2pair. So if values dot count, if the count of values where the value is 2 is equal to 2, then we have 2pair. Okay, so now we have 3 of a kind, 2pair, 2pair, and 3 of a kind. Okay, so this is looking pretty good. But instead of just returning a symbol for 5 of a kind, 4 of a kind, etc., let's instead like order these for our ranking. So let's start high card with 1. We'll make this one 2, 3, 4, 5, 6, and 7. Okay, so now we have some numeric representation of the type, and that will allow us to at least compare the type. So we can do type, rocket ship, the other type. So this will give us a comparison between the numeric value that we get back. So we should have at the beginning of a sorted list of hands, we expect to have the lowest type first, and then at the end of this list should be the highest type. So let's run our code again. All right, so now it's in order, right? We've got 2, and then, or we've got, a pair, and then we have two pairs, and then we have a 3 of a kind, and we have a 3 of a kind. So now the problem is we want to order these, or like the order of these two are incorrect, because when we have a tie based on the type, we need to break that tie based on the rank order of the cards and how they appear at the front. And this one is king, so that should come after king 10. So king 10 should be lower value than king. So now what we need to do is not only compare the type with the other type, and technically what we could do is say, give us some result and return R unless R is 0. And then we might say something like cards, compare with other cards. And if we run this, all right, so now we are in the correct sort order. Because we can compare arrays like this, so we can say 1, 2, 3, is that smaller than 10, 11, 12? And it is, right? We correctly got -1. But if we do 100 here, then it would say that this one is bigger and they need to be swapped. And Ruby or like the array comparator is pretty smart. So if these two match, then it knows that it needs to go to the next number in the list. And so now this says that these are correctly in order. And then again, if we change this one to 20, it should say that you need to swap them again, because now 10 and 20 is bigger than 10 and 11. What's cool about that is that we can combine our type with our list of cards into one object that is being compared from this hand to the other hand. So now we can do like other.cards, and we should be able to run this, and we get back our cards, and they should be in the correct sorted order now. All right. So the next step in the process is, now that we have them in rank order, now we need to go through and figure out the total winnings. So the total winnings are found by multiplying each hand's bid with its rank. So the rank is like where it appears in this sorted list. 765 is the bid for the lowest ranking card, so it's multiplied by 1. 220 is the bid for the second lowest ranking card, so we multiply by 2, and so on and so forth. So what we want to do now is iterate over our sorted hands. And for each one, sorted hands dot map dot with index. I think we can do this. And then we should get back hand and index. Let's just see that works as expected. Okay, yeah, so this is our index, 1, 2, 3, 4, 5 is I plus 1. So now we want to do I plus 1 times the bid, and we should get back like hand.bid times I plus 1. So let's see. Okay, so 1, 2, 3, 4, 5. 1 times that, 2 times that, 3 times that. And in our example, that's what it looks like. Okay, and now we can say dot, let's just grab the result and then print result.sum. And now we get 6440, which is the example total winnings for the example 5 cards. So now we need to grab our puzzle input here. We'll drop it at the bottom and run it against our example input. Oh, I guess now we need to switch data here to be data.readlines. And let's run this puppy. Actually, let's comment that out because it's the example data has quite a bit. All right, so 2500583, blah, blah, blah. That is the puzzle answer for part 1. Boom. Fantastic. Okay, awesome. That is how we solve part 1. We've got our manual ranking algorithm here, and then we're sorting by the type and by the cards that are in the hand or the ranks of the cards in the hand. So this is looking pretty good. For the most part, it's pretty clean. So let's jump over to part 2. All right, so to make things a little bit more interesting, the elf introduces an additional rule. Now J cards are jokers. So jokers are wild cards. That means they can pretend to be any other card. I prefer in Uno when the jokers are all colorful and they make it seem like you've got a fun hand. Also, if you haven't played the game Skippo, the card game Skippo, this is an amazing game. Like, I highly recommend this game. We play it a ton in our house, and it's just so fun. You can play mindlessly and visit, and the mechanics of the game make it so that you can play without having to say, like, I'm done with my turn, it's your turn, etc. You can just visit. So that is awesome. All right, so to balance the J cards, now the J cards are the weakest. So the rank order of the cards, if we're talking about the alphabetical order that we're going to use, it goes ace, king, queen, and then no J, no joker, or no jack, 10, 9, 8, 7, 6, blah, blah, blah. And then jokers are equal to a 1 in this case. So the first thing we want to change is we'll just make jokers worth 1 point. Okay. And then now, because they can pretend to be whatever they want to be, we need to be able to replace certain cards in any of our hands with jokers to make them the best possible card. So for instance, if you have queen, joker, queen 2, this is now going to be a 4 of a kind because you can say queen and queen plus the joker converted to a queen twice. Now you have 4 queens. So the way that I thought about this was, let me first grab out like the number of J's. So we're going to grab like a J count, or yeah, the joker count is how many cards are ones. I think we can actually just do 1 like that. And now I want to say non-jokers is cards where the card is not equal to 1. And we'll try to figure out what is our best hand without the jokers. And then we'll add in the jokers to get to a new rank that will be equal to the best hand that we could with those jokers. That's like my thought process, at least. So here I'm going to say non-joker cards. So now we want to group those non-joker cards. So the card counts here are going to be for non-jokers only. And then I want to be able to just use this joker count directly and say something like, okay, so let's think through each of these. So if there's 5, if there's any card counts with value 5, that's going to still be a 5 of a kind. So this is still good. So maybe we still say 5 of a kind. And if there's 4 of any value, then this is 4 of a kind plus some joker count offset thing, right? And if there's 3 of a kind plus 2 of a kind, then it's not really possible for there to be a joker, because if we have 3 of any card and 2 of any card in the list of non-jokers, then this must be a full house. And joker count doesn't matter in that case. Now, if we have a 3 of a kind, then if we add a joker, then it becomes a 4 of a kind. And if we add 2 jokers, it becomes a 5 of a kind. So we're going to need the joker offset there. if we have 2 pair, and we add in 1 joker, that becomes a full house, right? And yeah, so this becomes full house. And then if you have 1 pair and you add a joker, you get a 3 of a kind. You don't get 2 pair, you get 3 of a kind. So you jump over 2 pair. And if you add another joker, you jump over full house and you get 4 of a kind. And then if you have, high card, and we'll have to figure out like plus joker count here to figure out what we want to do. So if we have 5 cards, period, the way that I thought about this was like the easiest way to get this joker count to squish in here is to just think about, maybe if we think about 4 of a kind, right? If we want to go from 4 of a kind to 5 of a kind, we want to go 1 up, right? If the joker count in this case is going to be just 1, it's either going to be 0 or 1. So if we have 4 non-jokers and they're all, let's say, 2s, so we have 4 2s, and then if the other card is not a joker, then the joker count is 0. If the other card is a joker, then we want it to go up 1. So we're going to go to 5. So let's just pretend for a second that 4 of a kind here is 4 plus the joker count. And in this case, because the joker count can only be 1, that kind of makes sense for this to be 5, because we want a 4 of a kind plus a joker to be the same as a 5 of a kind, right? This needs to be 4 plus 1 to get to 5 so that we have some equal number. Now, if we have a full house, let's actually come back to full house first in a second. If we have a 3 of a kind and we add a joker, that should get us to 4 of a kind, which is the same as 4. So if we go 3 plus 1, that gets us to 4 of a kind. Same thing with a pair, right? So if we have a pair and we add 1 joker, that gets us 3 of a kind. If we have a pair and we add 2 jokers, that gets us to 4 of a kind. And if we have, 3 jokers, that'll get us to 5 of a kind. So this kind of works. And then for the high card, this one's kind of interesting, right? If you have 4 cards and none of them are jokers, and you add a joker, then you get a pair. So you would think 1 plus joker count. So let's keep thinking through this though. So if you have 5 jokers, then 5 plus 1 gets you too far, right? We don't want it to be more than 5. Maybe we want to do the min of the joker count plus 1 and 5, because we don't want it to ever be more than 5 of a kind. Now here, this one is interesting, right? Let's say we're going to start at 1, 2, 3, 4, 5, and then in between 2 and 3, we have these other ones. If we do 2.5, which is between 2 and 3, I think, okay, so let's think about this. So if you have 2 pair, right? So you have 2 pair and you add 1 joker in, you should get a full house, because then you'll have 3 of one and 2 of the other. So you'll get up to a full house. And okay. So if you have so let's make this 3.5. All right. So 3.5, it doesn't matter. We don't need to add a joker count, because if you have a full house, then you don't have any other jokers. And if you have 2 pair plus a joker, then you get a full house. I don't know if you're following this. This is wild, but let's see. Okay. So I think this is going to work. I don't know. Let's run this. That is our main data. Let's see if we run it against our example data. 5905, and we get 5905. Hey, that is the example answer. So let's change it back to our answer. 250, 506, blah, blah, blah. Boom. Okay, that's our answer for part 2. So that is how you solve day 7 of the Advent of Code in 2023. What can we do here to make this even better? Just for fun, why don't we try to make this all in a pipeline? All right, there we go. So super, like we're just code golfing at this point, right? So instead of passing in these arguments here, what we can do is use the numbered arguments, and that can make this even shorter. And now we're just getting wild. And all right, so that still works. This is pretty cool, using group by and transform values in order to create a histogram or a counter dictionary of the non-joker cards. The other way to do this, or like an alternative, would be to say like h is hash.new with these like default value of 0, and then we would say non-joker cards.each, increment h at that position. I guess this would be better called card counts 2. And so now here we have card counts. Actually, yeah, we'll just comment this out. And this should be functionally equivalent also. But I really like this group by itself and then count. That's pretty cool. Yeah, so we talked about comparable and the spaceship operator. Hopefully that was useful. Thanks so much for watching, and we'll see you in the next one. Cheers.